right, we'll go ahead and get started. I have some housekeeping today to let you know what's going to be coming up in terms of your exam. So the midterm exam is coming up. It's not immediate. It's 2 weeks from today. So it's going to be on the 19th of February on a Friday. I'm planning to do 40 multiple choice questions for OCS 2005. And you know sometimes I put those weird multiple choice questions where you have to select more than one right answer or select the best answer. So that's what I mean by multiple choice as well. And then for 2006, it's going to be a little bit shorter because I'm going to mix in some short answer questions as well as multiple choice. I'm going to, as I mentioned before, give you the exam questions to study from. All of my exam question test bank will be available to you starting on Monday. The questions are going to be provided to you in the form of a practice exam on Top Hat. So I'm not going to give you a Word file. I'm going to give you a practice exam to work through. You can go through it as many times as you want, but the correct answers will not be marked. So it's up to you to decide from your notes, from working with your classmates, from talking to me, what those correct answers are. You're allowed to work together to figure them out. I encourage study sessions, and you may use my Zoom room for them. So I leave my Zoom room open. Hopefully this doesn't come back to bite me, but I leave my Zoom room open. So if you want, you can go ahead and use it to study. There are going to be far more than 40 questions on the practice exam. I'm giving you my whole test bank. You're going to be asked a subset of the questions that I'm giving you, and the answers will be randomized. That means you're not going to be able to just memorize like, oh, the question that involves the Gulf Stream, the answer is going to be A. You'll actually have to know what the answer is. And each student might have different questions on their exam because I'm going to randomize a few of the questions and have like different options for them. The exam's going to cover everything through Lecture 12, Essential Fish Habitat, so that's going to be what we're covering next week on Wednesday, including some questions from the in-class activities and the assigned readings. I try and make it very obvious what I'm going to ask questions about on the slides, so you don't have to go back and listen to my voice recording over again to get the information you need to answer these. You'll have 2 full class sessions to study. These are going to be optional for you, but they're actually like taking the place of class on the days of 212 and 217. So those are the 2 class periods that sandwich the day that you get off for Mardi Gras. And I will help you figure out the answers to any questions that you have issues with during these sessions. You can also come during office hours or ask me over email. So you should have lots of time to work through these questions, figure out which ones that you aren't quite sure about, and we can come up with the answers to those. The exam is going to be on February 19th, 2 weeks from today. I'm going to open it at 10 o'clock, so open it a tad early. For those of you that don't have morning classes before this and that want a bit more time, you can hop on at 10 and start. You don't need to log on at 10. You can drop into Top Hat whenever you want to take it from 10 until noon. So I'll leave it open a little later than class as well for those of you that don't have a class immediately after this. You are expected to complete the exam on your own, even though you can study with others. I want you to make this exam your own work. I'm expecting you to do it without notes, but I'm not proctoring it, so I'm just asking you to please be honest. And you may have accommodations if you want. Just ask if you want to take it a different day, if you want more time on it, if you don't feel like you had enough time and you want me to open it up to you again sometime, after the exam period. Any of these things, just ask me. We can make it happen. That's the nice thing about being flexible and virtual is that I could just click a button and open it up for you again. So just let me know. Any questions about the exam in 2 weeks? Okay then. You can ask me if you think of something. You'll have plenty of time to ask me questions, because like I said, we're devoting 2 full classes to studying for this, so I think that this will not sneak up on you. Alright. Today we are going to cover coastal habitats. We have, including this lecture, we have 3 more left that will go on your midterm exam. So we're, getting already into the middle of the semester. That seems not right. That seems pretty crazy, but it's the truth. So today we're going to cover ecosystem functions and services, intertidal zonation, some common coastal habitats, and we'll discuss some ways that natural habitats can be used as utilities. Learning goals for today are to cover ecosystem services, to understand that they're aspects of an environment that provide benefits to humans. We'll learn that coastal habitats are characterized by zonation. We'll learn that wetlands filter chemicals and particles out of runoff water before it reaches open water. That carbon and greenhouse gases are stored in coastal habitats instead of being released into the atmosphere. We'll learn that in many places, marshes protect shorelines better than walls and are cheaper to construct, actually. And finally, that coastal habitats shield people and property from the impacts of storms. So up until this period, we've been talking about mainly physical and geological oceanography as it relates to the Gulf of Mexico and coastal features. We've also had a healthy dose of culture and history, but most of our oceanography has been looking at physical and geological oceanography. We've looked at the origins of coastal features, at physical phenomena that define the Gulf and its estuaries, such as currents, tides, and seasons. And I think you have a pretty good idea of the physical and cultural building blocks of the Gulf at this point. So we can launch more into how the Gulf of Mexico functions, how people are related to those functions, and how they have changed over more modern times. So if you look in your syllabus, the first several lectures up until this point were devoted towards a module on origins, and now we're moving out of that module into the next one. And the next module is going to be ecosystem functions and services. So the next 8 lectures are going to cover ecosystem functions and services. And when I say that, I mean the following. So ecosystem functions are the aspects of an environment that control how energy and matter flow through that environment. So we'd be talking more about food web dynamics or nutrient cycling. Those would be ecosystem functions, especially aspects of the environment that control how fast those exchanges of matter or nutrients or whatever, how fast that happens. And then ecosystem services would be aspects of the environment that specifically provide benefits to humans. They could be ecosystem functions, but they have to be related to humans in order to be an ecosystem service. So I have here several categories of ecosystem services. This really wasn't meant to be just for marine systems. This is meant to be for all systems, but you can see how many of these are very much something that can be covered by marine ecosystems, like erosion prevention, protection from natural disasters, air and water pollution control, recreation and tourism, certainly. So, marine systems are under the same branch of providing a lot of ecosystem services to people. So of course we're talking about coastal habitats in this course, and we'll be talking about them a lot in this lecture as they relate to ecosystem services in particular. Coastal habitats are some of the richest environments on Earth. They are associated with both really important terrestrial and marine ecosystem functions, so you kind of get the best of both worlds in coastal systems. They also have among the highest biological productivity, and they support large and diverse biological communities. And we'll have an entire lecture on coastal productivity moving forward. So that won't be our focus today, but it's important to note we're talking about coastal habitats, we're talking about very, very productive regions. This image here is showing you the global distribution of some coastal habitats around the world. So we have kelp in green, seagrass in yellow, mangroves in black, and salt marsh in blue. The East Coast is largely depicted here as being a seagrass habitat, as well as the Gulf Coast. But I can tell you right now that both the East Coast and the Gulf Coast have extensive salt marsh, so this isn't entirely accurate, but we'll get a better picture of what this looks like for the Gulf Coast at least in this lecture. One thing that really unites all coastal habitats is that they're characterized by zonation. So these are habitats that are happening somewhere near the intertidal zone or in shallow water or slightly above the intertidal zone. And so in some way, shape, or form, all of these habitats are either impacted by the tides or they're impacted by shallow water environments, which have a lot of vertical zonation in and of themselves, with temperature and with light. So if we're talking about a coastal habitat that exists in the intertidal zone, that's going to be the area between high tide and low tide. It's going to be subject to daily inundation and drying because the tides are going in and out in this area. And so we might expect, for instance, to see some marshy kinds of habitats happening in those areas. A supertidal zone is just above high tide, and these areas are affected by salt spray or storms. And so oftentimes we get some sort of scrubland that's happening just above the high tide line. And some marsh also exists just above the high tide line. The subtidal zone is going to be below low tide. So this is going to be an area that's always submerged, generally in really shallow water. But as I mentioned, even in shallow water, you get zonation. You get zonation by light availability and often by temperature. So in this picture, we have some seagrass here in the water. This seagrass is existing in an area where it has enough light, but it's not too terribly warm as it is in the really, really, really shallow area. So you get zonation by light availability and temperature in the subtidal. Many coastal habitats can contribute to even just one coastline. And so because you have all this zonation, you can have something like an offshore oyster reef, you can have mangroves along the shoreline, and then salt marsh stretching far inland. So you can have more than one habitat in a coastline. Mangrove and salt marsh are really the dominant types of intertidal wetlands in the Gulf of Mexico. So when you're looking at the coastline in the Gulf of Mexico, usually you're looking at mangrove or salt marsh, or both. This image here is showing you common areas where you can find mangroves in yellow. So you can see here, like for instance, around the tip of Florida and along the Florida Keys, you see a lot of yellow, as well as around Cuba and the coastline of Mexico. And then salt marsh is in red, and salt marsh you would commonly find along the Louisiana coastline and parts of the north coast of Texas. Salt marsh is dominated in the Gulf of Mexico by a couple of species of cordgrass. So they look like tall grass, kind of like ornamental grass, but they need wet feet, so it's not quite the same as the ornamental grass you would find in your yard. It does look similar though. And then there are 3 species of mangrove in the Gulf. We get red, black, and white mangroves in the Gulf. So at this point, I'm going to have you do an assignment related to mangroves, looking at their distribution and how that changes with climate. So if you want to go ahead and hop in Top Hat under week 4, 10 in class, you're going to find the Mapping Mangroves assignment. I've also included a PDF there that's showing you the images of mangrove distribution in case you want to like download that and just have it handy. Those pictures also appear in the assignment itself, but I know sometimes it's easier to work from a PDF. This is not a terribly long one, so I'll give you until 10:55 and then I'll check back with you like I normally do. Alright, I think I have most of your answers in. So what I was trying to get at here is that really, really bad winters tend to result in mangrove contraction over time. And then mild winters tend to result in expansion. And so this last question, when you're talking about the prevailing climate and how that might kind of explain some of the expansion and contraction that you saw. So I think it's best illustrated using the image from 1979 to 95, because during this time period there were a few really kind of, extreme years in terms of winters. We had these 3 years that happened within a decade that had some of the maximum days with the minimum temp below freezing, 5 days in a row. Then perhaps more concerning, we had some years where you had, 3 days in a row, consecutive days where the maximum temp was below freezing. So these would be some pretty serious cold events that could result in mass mortality of mangroves. And so during this time period, from 79 to 95, you saw mangrove contraction. And then from 95 onwards to 2004, you can see that there were some really mild winters, including in 95 where there weren't any days that were below freezing. And this allowed for the mangroves to expand. Mangroves are a tropical species. They don't like a lot of cold. They only exist in the tropics. So they would be needing, these tropical temperatures to really thrive. So we talked about salt marsh, talked about mangroves. Next habitat I want to cover is seagrass. So seagrasses occur in shallow, low energy, clear water lagoons and bays. There aren't too many of those in the Gulf of Mexico. So seagrasses tend to be found along the coasts of Florida, southern Texas, Mexico, and Cuba. We don't really get any up here around the Mississippi River, and there's a good reason for that. So seagrasses are not algae, they're actually flowering plants. As plants, they need a lot of light to thrive. So they don't do well in muddy water. They would not do well close to the delta, where you get that muddy plume that spreads out and could potentially leave them without light. We do have a little bit of seagrass in coastal Louisiana and the Chandeleur Islands. I really want to go there and do some snorkeling. That would be so cool. We have 6 species of seagrass that are common to the Gulf, so we have pretty high seagrass diversity here. The next habitat I wanted to cover are oyster reefs. Oyster reefs in the Gulf are made up of one species, and that's the eastern oyster. And the eastern oyster's distribution is really limited by salinity. They like estuarine salinities, not full-strength seawater. And so you really only find them in areas that are able to provide that, mix of saltwater and freshwater. And these tend to be in the larger bays. So like Mobile Bay, Breton Sound, all of these larger features, larger coastal features that we learned way back when we were looking at coastal features in the Gulf. That's typically where you find oysters. Interestingly, the Gulf is one of the only regions remaining in the world where there is still a fishery for wild native oysters. In most other places, all oysters have been overfished to the point that they don't exist in wild reefs anymore. In the Gulf of Mexico, that's not the case in these regions that are outlined here, like for instance in coastal Louisiana and in some locations in Texas. That doesn't mean there's no oyster harvesting in other places. It just means that people harvest oysters through aquaculture. And in the Gulf of Mexico, oyster aquaculture is also a big deal. So it's not just the wild oysters that get harvested and consumed in the Gulf of Mexico. We also have a booming oyster aquaculture business here. So, speaking of oysters, I wanted to talk a little bit about some of the ecosystem services that some of these coastal habitats offer to humans. And you can't talk about oysters without talking about water filtration. In fact, there are a lot of different coastal environments that will filter water. So as sediment, excess nutrients, and chemicals flow off the land through coastal environments, wetlands and different coastal species will filter the runoff before it reaches the open water. They filter a variety of things out of this runoff. For instance, nutrients can be stored and absorbed by plants or microorganisms in the marsh. Sediment will settle at the bottom of the wetland after reaching an area with slow water flow. And we learned about that in our last lecture when we were talking about deltas and floodplains kind of trickling and spreading out over, water spreading out over a floodplain, slowing down, dropping sediment. Water does the same thing as it flows over a marsh surface. And then, as I mentioned, oyster reefs are also really good at filtering. So they clean water through their normal feeding activity, their filter feeders. A single oyster can filter 180 liters of water every day. It's an insane amount of water. Particles are ingested, digested, and deposited as feces. And this is important because the feces are relatively heavy and so they sink. And that means they get incorporated and stored in coastal sediments. And we'll talk about why that's important in the next few slides. Taking particles and materials out of the water and putting them into the sediment. So that leads us to carbon storage. Coastal environments are really, really important for storing carbon and greenhouse gases. And when they do this, when they store carbon in coastal environments, that prevents that carbon from being released into the atmosphere as CO2. So it's solving some of the global greenhouse gas problem. If we're talking about carbon stored in coastal ecosystems, like mangrove forests, seagrass beds, and salt marshes, to name a few, the term that we use for that carbon is blue carbon. Carbon stored in coastal environments. Vegetated coastal habitats, like those that I mentioned, are disproportionately important in storing blue carbon as compared to terrestrial forests. And there's a reason for that. So, like terrestrial forests, these are plants, and so they're trapping CO2 to create tissue, producing oxygen through photosynthesis, and so they're able to trap some of that carbon in their leaf material. But coastal habitats do something that trees don't. So coastal habitats are very good at trapping suspended matter and associated organic carbon from that suspended matter out of the water during the tidal cycle. So they have this extra function that allows them to trap more carbon, and that's why they're so important. And as I mentioned, trapped carbon is buried, and it does not contribute to greenhouse gases, at least not for some time. Carbon burial is not forever, but it does help with the immediate problem of climate change. So this is showing you that carbon burial in coastal habitats like salt marshes, mangroves, and seagrasses occurs at a much higher rate than in terrestrial forests. Of course, there are more terrestrial forests than there are salt marshes, but it's important to note that if you're going to destroy habitat, destroying coastal habitat puts you at a lot more risk of releasing some of these greenhouse gases into the atmosphere. So delving a little bit more into blue carbon, I wanted to talk about the valuation of carbon, and this is kind of some extra material for the honors folks, but some others of you might find this interesting. So if we're talking about reducing carbon emissions, not all operations can reduce carbon emissions. There are factories and processes that produce carbon that cannot be made more efficient, or they can only be made so much more efficient. So there's like a limitation to that. And so these companies, these organizations, these people must buy carbon offsets to meet their emissions regulations requirements. And a carbon offset is a reduction in emissions of carbon dioxide or other greenhouse gases that's made in order to compensate for emissions made elsewhere. And so you're reducing carbon somewhere, and that will make up for the carbon that you're emitting elsewhere. This means that we have some sort of value associated with reducing carbon or storing carbon, and it creates a market for valuing carbon offsets. Companies that are interested in meeting their emissions targets by buying carbon offsets can be supplied by people who are interested in producing those offsets by reducing carbon in the atmosphere through things like planting salt marsh that creates a sink for blue carbon. The capacity for coastal habitats to store carbon makes them extremely valuable in a carbon market. If you're going to decide between planting trees or planting salt marsh, because that salt marsh is able to trap a lot more CO2, you don't have to plant as much of it in order to make a lot of money selling carbon offsets. We're still kind of in the early days of valuing carbon as a culture. This image here is showing you a couple of different markets that have been trying to value carbon over time. The green one here is the verified emissions reduction market, which was a voluntary market, kind of like just a free market that popped up in capitalist nations. And it did quite well for quite some time. This went from around 2003 all up until 2010, and then it kind of bottomed out. And then there was another market trading scheme called the Certified Emissions Reduction. And this one in blue here is a scheme created by the European Union in response to the Kyoto Protocol. And you can see that carbon was trading quite high for a while. So this could influence people to join the market by producing these carbon offsets because there's a demand for them and the cost is high. But unfortunately, towards the, after 2010, this market also started to decline. So there has to be a lot more invested in creating and maintaining these carbon markets in order to create a place where you can sell these offsets and make it profitable. And if it's profitable, people will do it. So it's going to be interesting to see how this kind of evolves over the next couple of decades. All right, moving on to another ecosystem service or another utility that nature provides. Erosion prevention. Coastal homeowners typically construct concrete barriers to prevent erosion of their land. I'm sure that you guys have seen some sort of concrete barrier along a lake or along a marsh or along a city harbor that would prevent any sort of land adjacent to that barrier from falling off into the water. In many places, a living shoreline would be able to protect coastal developments even better than walls, and these living shorelines are even cheaper to construct than a seawall. And by living shoreline, I mean a protected, stabilized coastal edge made of natural materials such as plants, sand, or rock. This is an image here of a typical living shoreline. There's almost always some sort of marsh grass associated. Usually there's a planting of marsh grass. And then oftentimes there will be these kinds of break walls that are made up of some sort of natural material, in this case, oysters. I've seen them also made of wood and also some rock, but usually if rock is used, it's used in such a way that it will create habitat for things like oysters in the future. The nice thing about living shorelines is that they can grow and respond naturally to dominant flow patterns, while hard barriers don't do that, and they can be undermined and break down when they're overtopped by waves. So as we learned about marshes, when there's flooding that's happening, there's sediment dropping out into the marsh, and the marsh will grow up vertically to keep in sync with that flooding. Cement barriers would not do that. So cement barriers would be flooded. There would be some sort of erosion, usually on the backside of the barrier. They become undermined and they break. Oyster reefs will limit erosion and flood damage by acting as natural breakwaters. For instance, they can be offshore seawalls. And when they're there, they disperse wave energy as waves pass over them because they have rough, broken up surfaces. So these surfaces will baffle that wave energy as it passes over them. And it's been shown that about 15 meters of salt marshes and mangroves, with their roots and stalks, can remove more than 50% of the energy out of approaching waves, even during a pretty big storm. So removing these coastal environments can result in more vulnerability to these storm events, as we have seen over time, unfortunately, in the Gulf especially. And we'll talk a lot in the future about marsh loss. We have a whole lecture on it. We'll talk about the impacts to coastal people then, but this is a very important ecosystem service, so I definitely want to mention it now. And a natural next thing to talk about is nature as natural storm buffers. Coastal habitats, in addition to reducing erosion, they can shield people and property from the impacts of storms. Vegetation like mangroves and salt marsh reduce hurricane winds by increasing the surface roughness. Vegetation can also serve as a physical barrier for surge water, protecting the coastal dwellings from dangerous storm surge. So this is how this works. As a storm surge approaches, that mangrove habitat can serve as an actual block. So you see increased storm surge on the seaward edge of the mangroves, and then hardly any storm surge on the landward edge, which is exactly what we want to see for those homeowners who would otherwise be flooded if the mangroves weren't there. This is an image of this actually happening during Hurricane Wilma. This pink line here denotes the edge of the mangrove habitat, and these lighter, or these warmer colors here denote the highest part of the storm surge. You can see the storm surge was highest right at the edge of the mangroves, tapered off to almost nothing as the storm approached land. That's exactly what you want to see from your coastal habitats. The effects of vegetation on the air and water flow can be accounted for by the drag force. I don't talk too much about physics concepts here, but I think this one is pretty easy to grasp. So it's just the resistance force caused by the motion of a body, in this case we're talking about plants, small trees, through a fluid such as water or air. So these mangroves, just by being physical structures, can disrupt the flow of winds and also currents and surge. All right, in the last 5 minutes, we're going to have a quiz question, just one question today. Feel free to log off afterwards because this is the last thing that I'll have for today's class. And if you do, I hope you have a great weekend. This is kind of a long question. I apologize. Okay, I'll read it for you. There's a public comment period opened up by your local city council, allowing you to comment on a proposal to convert about 25 meters of mangroves and salt marsh into a series of cement seawalls and offshore rock breakwalls to protect a new development from storm surge and land erosion. You think this effort might be misguided. From what you learned in this course, how might you reply? More than one answer may be at least partially correct. Please choose the best response that addresses the major changes proposed by your city council based on what you learned in class.